So these examples, we have a horizontal beam, fixed support at the, if we say this is point A, and have a red end, this is a roller support, we see this roller support D, and we have a hinge on the beam. So if we say this point is B, and we have a concentric node applied at the center of this right hand segment, beam segment. So if we say the support is C, so the question is we need to calculate the vertical deflection beneath the applied node. That means we need to calculate the deflection at point C. So because the deflection at point C, we have a concentric node. So this deflection is at the loading position and along the loading direction. So then we can apply the work energy principles to solve this problem. I also call this is method of real work to solve it. Okay, so to solve method of real work, that means the work done by the external node 1/2 p delta. So if the delta as deflection is delta, so delta is equal to the strain energy stored in this beam. So the strain energy is 0 to L. So L here is 3L. So 3L and m squared over 2EI dx. Okay, so this is the equation to calculate the deflection at point C. So look at this equation. We know the node is P. We need to calculate the delta. And so we need to evaluate these integrals. Okay, look at these integrals. So we don't know the bending moment, internal bending moment. So we need to find out internal bending moment. So here the question provides the bending moment diagram is showing here. So is from, this is a linear curve change from the minus pi/2 to pi/2 and then change to 0. Okay, so first of all, look at this bending moment. As we know, we need two functions to express this bending moment. So one function is for this line, the second function is for this line. Okay, so if we say this function is m1, this function is m2. So if we can find the function of m1 and m2, and they are expressed by x, well, then we plug in the function into these integrals, then we can evaluate these integrals. So next step, we need to find out the function of m1 and m2. So if we want to find the function of m1 and m2, we need to build up a coordination system. But here we already have a coordination system over here. This is y, this is x. But this is not good to help us to find the function. So now I would like to build a new coordination system to help us to find a simplified expression from m1 and m2. So for m1, I built a coordination system here at point B. So this is y, this is x1. Okay, so if I put the origin of the coordination system at the point B, then we can easily express m1 is equal to p/2 x1. Okay, you can easily find the curve. This curve m1 can be expressed by these functions of x1. So if x1 equals 0, then bending moment equals 0. If x1 equal to negative L, equal to negative L, so the bending moment is equal to minus PL/2. So if F1 equal to L, then the bending moment is equal to PL/2. So this is M1. Then we need to find M2. Okay, so I would like to put the coordination systems new coordinate system. I don't want to use in the y-x1 because this is not easy to find the function of M2. So I would like to build a new coordination systems. So the new coordinate systems over here is next. So this is x2, this is y2. Okay. So based on these new coordinate systems, the origin of the coordinate system is at point D, and M2 is this line. So we can easily find out M2 can be expressed by negative p over 2 x2. x2 equals 0, then bending moment equals 0, x2 equal to, so here the point is x2 equal to negative L. X equal to negative L, then we plug in, then M2 equal to PL over 2. So once we got the expression for M1, M2, then we plug in this expression into the integrals. Then we evaluate these integrals. So what are we gonna do? So we're gonna do for M1, M2. So the integral for M1 is the x1 change from negative L to positive L, and the p over 2 x1 square over 2ei dx. So this is for M1. And M2, the x2 change from negative L to 0, and M2 is PL over 2 x2 square over 2ei dx. So these two integrals is just used to express this integral together. Look at here. Look. So these integrals, we x change from 0 to 3L. These integrals is built up from these coordinate systems. So the origin of the coordinate system at this point. But now I changed the coordination system to two separate coordination systems. Then I write down these two integrals. Now we need to evaluate these two integrals. Then we will have, so for this one we write down over 2ei. Then we will have minus L 4p square L1 square dx1. So dx1 dx2 plus 2ei. We just put 2ei outside of the integrals. Minus negative L 0 p square 4 x2 square dx2. Then we write down here 2ei. So we evaluated these integrals. We have 12 p square x1 cubed L to L plus, so we got 1 over 2ei over here. So then we got 12 p square x2 cubed negative L 0. Then we got result is 1 over 2ei. So this is 6 p square L cubed. And if we evaluate this one, we will get plus 12 p square L cubed. Okay, then we got the result is, we will find the result. If we can evaluate this was 1 over 2ei, and then 4 p square L cubed is equal to 8ei p square L cubed. So this is the final result is here. Okay, so it's p square L cubed over 8ei. Okay, we know this is equal to p square L cubed 8ei. Okay, so this is the equation. This is the equation. Then we divided both sides of this equation. Then we got and we got dirt equal to P squared L cubed 8EI divided by P over 2. Then we got dirt equal to 4EI PL cubed. So this is a final result for the deflection at point C. Okay, this method is work energy principle, or we call this method of real work. We will try other methods to solve this deflection as well. Please check the following videos. Thank you.